Pachinko, and tonight we're wrapping up our differential equations class. We have both of our co-hosts slash guests slash awesome people on the line. So Zach and Stucky, if you would like to introduce yourselves. Certainly not for the last time.
Sure. I'm Ian Stuckey. I stream over here on Twitch, and I also run a newsletter called No Royal Road about geometry study problems.
I'm Eat of the 2i Pi, Zach over at Eat of the 2i Pi on Twitch, and I am currently running an infinite series class where we're studying all sorts of stuff with infinite series and connecting that to real analysis and other stuff. So, yeah, that's me.
Awesome. All right. So tonight, because we're just kind of wrapping up our differential equations class and talking about the we're not really doing any content tonight unless anybody has any like massive either revelations or something that they want to throw out there. But we won't be doing content for a bit, and then once we're done with our discussion, our guests are going to have the gift of time, if you will, and we will then work on a bit of content with some of our other people.
Sounds good.
Wonderful.
All right. So, first question. How do you think the class went?
Broadly speaking,
We'll get more specific as time goes on, I'm sure.
Yeah. I mean, I enjoyed myself. Let's start there. It was and you've remarked on this a couple of times, it was a little twist order-wise, and I thought those experiments were interesting enough for me to appreciate, having seen the material. It's been a while, but
Yeah.
but sort of still remember vaguely how it goes. Or sort of the traditional path through this content. So yeah, I appreciated that. Participant?
Let's see here. So, like, this actually is reminiscent of, I mentioned, I think before, that I got to teach this class once at my university. And when I taught it, it actually mirrored a lot of what you did. There's a lot of similarities about, for example, teaching first-order systems first, and then using that to build higher-order equations. I think there's an advantage in doing that, and actually some research. There's actually a project called the Inquiry-Oriented Differential Equations project. There's several who do this, but I think it's out of University of Nebraska. Is that right? Who has put together this curriculum? It's the one I used when I was teaching the course, and I loved it. And I appreciate that the second-order systems built off of, or second-order equations built off of first-order systems. I think that's a logical way to go.
Yeah.
And some of my more favorite topics on being able to talk about the stability or instability of solutions and being able to talk about phase planes and such is a nice touch, getting into that kind of dynamical systems. I really appreciated that part of it.
Yep, and as I said during the course, it was mostly a product of this guy, Pavel Grinfeld, who wrote Introduction to Tensor Analysis. The series that I was actually watching was from Lemma, which is a summer camp sort of differential equations oriented a high-level math-oriented program. And his particular class was partial differential equations for high schoolers. So it was quite interesting to try to remember all of the stuff that I'd learned in my PDE class.
I mean, I'm sort of curious what your goals for the class were. Like, what was the thing you wanted to do? Hey, this is actually a question that whenever we did lessons in my as a pre-service teacher, it was something that my university supervisor person, the instructor of the course, always asked, and I hated it, but I'm going to ask it to you because I feel like it's important. So, like,
Zach,
what
why?
did you? Right? These are the questions that you hate. But like, what were your goals for this?
That's
course?
absolutely no. I mean, that's fair, right? Because we do want to know, as educators, how exactly are we structuring all of this? What are we doing? So I think first and foremost, I just wanted to kind of get out there in the same way that, you know, Zach, you'd gotten out and said, I want to do real analysis. You had some other goals. I also had some other goals, just practicing, making sure that I'm keeping myself active with teaching because, you know, otherwise I'm here. In the UK, I'm not with a particular class, and yeah, I could probably teach for University of Leeds or something like that, or, you know, find an online class that would be happy to have me. But at the same time, I also like the kind of lack of structure and or forgive me, accountability.
Right.
That being online and just being able to say, hey, what do I feel like teaching today? Now, granted, this was a more structured class, right, where I took my curriculum from my actual differential equations class that I taught last in, well, according to this, 2020, and wanted to kind of play around a little bit and see not just only let's just redo the class, but also let's see if we can get a few more topics in that are a little more interesting. Let's see if we just kind of go on tangents for a little while, because we can do that. We have time. In a lot of our math classes, you just don't have time because you need to get through content. And I know, right, Zach, you've mentioned this before, where that's just kind of not great, especially in terms of
the not greatness. The what was that? I missed the antecedent.
No, that's all right. The need to get through content is not
yes.
like a really great motivator, whether for teaching or for being students.
Sure.
I wanted to kind of bring in also the at least a little bit of the building thinking classroom stuff that I've been working with for the past couple of years. Wow. Okay.
By the way, I'm just going to put this out there. If either of you are interested, I'm open to this. I would love to do something math ed like in the future, where we get a group to talk about this stuff, because I would love to, like, I don't even have to be the leader here. I just like to be a part of it. But I would love to be able to do something where we dive into something like Peter Liljedahl or some other thinkers. Like there's loads of people we could do. That's sort of one area I'm pretty good at. I like to think, and but it's something that I mean, these kind of conversations and what education can be is super interesting to think about. So I completely am with you on that.
For sure.
Those?
I'm looking at your camera. Yeah, there you go. That's the kind of stuff. Yep.
Yeah,
I
the
recognize
challenge to care in schools, Nell Noddings, learning to teach for social justice, Hammond Lopez, teaching Gap, Stigler and Hebert, and Gardner's Intelligence Reframed.
Oh wow. Okay, so quite a bit there.
Yeah, I mean these are 20 some odd years old at this point, but
right. Well, and there's like I have a whole collection of books too that I like. Among them is Peter Liddell's work about building thinking classrooms, and actually, my wife got to read that and implement some stuff for her classroom this last year. So, like we've had frequent conversations about that in our family. But
what does she teach?
I find
or what level?
That? At high school.
Yep, nice.
So it's sort of nice to. But anyway, these are interesting conversations. But my point was to connect to what you were saying and say, there is this room to explore, and I'm totally. I sort of find that interesting about the format you chose. So I'm gonna. I don't know how candid do you want me to be on camera? Do you feel comfortable?
No. Look,
it's like I have.
Anybody can go back. Anybody can go back
right.
and see where it was that I stumbled and tripped and did all sorts of stuff.
No, I get that. I'm just saying. I mean, I prefer how I guess what kind of criticism would you like? Is there any? I have some things I could say, and we can talk about this more privately later or whatever. But I'm totally.
I'm not too worried about it. So.
Okay.
Go for it, Zach.
So one thing there's one thing. I would this is perhaps this is just my bias.
Okay.
I find it helpful when there's I first of all didn't know what to expect coming in. I was like, I don't know, because with you and Penn Center doing this, it was sort of interesting to see different takes on what education can be. And I've been in tons of different classrooms, but one thing that I like to do is always have some kind of almost a motivating question. And I wonder or some kind of, I don't know, I wonder what a class would look like that looks like this, where you had some kind of motivating question come in, because sometimes we'd come in and I felt like I was guessing a lot and I didn't know what kind of what I sort of didn't know where you wanted to go with stuff. And perhaps if there were some questions that could motivate that discussion, and maybe you still don't say stuff, maybe you still have this thing you want to talk about, but perhaps if that conversation naturally flowed from the problems you gave, and maybe there was a sense of okay, maybe this is, that's just my bias because you see how I run the stuff I do on Twitch.
Yeah.
But I wonder how to make that kind of thing. I felt like I didn't know what to say at times, if that makes any sense at all.
Yes.
And I said this frequently, but I don't know how else to say it. I feel like there were moments where going through it, I didn't know where it was going. I didn't want to spoil too much or go in a direction that was unproductive. And it felt like there was a thing you wanted to get to that I wasn't hitting on at times. And it was almost like I was being led. The witness was being led, if you will. I'm using legal terminology.
Yeah.
I don't know. These are all just musings on my part. I don't know.
No, I completely understand. And a lot of the sessions that you had for Real Analysis, right, there was a very clear sense of what we want to cover for the day, or at least what direction we want to head in. And I definitely appreciated that. I don't know that I mean, obviously I didn't take it to heart.
No. Well, and neither were you supposed to necessarily. I'm not saying, I'm expressing my bias out as a, putting it all on display for you.
Accomplished.
So, accomplished. I was going to say, that's exactly my goal. But I wonder though, it just sometimes felt like I I wanted a little bit more of like a structure, and maybe it's just because I haven't experienced something like this before, and that's totally what's cool about this platform, is that we can experiment and like try something, and maybe that resonated differently with others. I'm not saying that I like this is one voice talking, so
Yep. No,
so
understandable.
like take that with a grain of salt.
But there were certainly times where Stuckey and I were having the same sort of interaction, where it was kind of like, well, I don't really know where this is going. I know what, I know what you're saying, but I'm also somebody who's taken this before, and
and this is like, we can talk about this more if you're interested. I just wonder, like, that's like, if anything, I think a little more structure could be helpful. But I overall think that if you think about the content you would quote unquote cover in a course, I think you did a lot of what a standard introduction to differential equations did. And so in that sense, I think you accomplished a goal, that in 19 meetings, you've been able to do what a normal 3-credit course would do. So hats off to you there, and bravo.
Thank you. I had very helpful partners in crime here. So.
Well, but still, you had to do a lot of the prep work yourself, and I think you shouldn't discount that. So, Again, job well done.
Thank you. Yeah, I definitely need to update my notes, because some of them were most certainly outdated, and had a couple of holes in there that we unfortunately found. But I have taken more careful note of where those problems were, and I think probably I tend toward slightly unstructured, just because there's a few reasons. One is that I tend to be able to there's a Bruce Lee quote, "Be like water."
Right.
Where, anything that comes at me, I tend to be able to kind of redirect into a question, or use in a Socratic manner, such that I'm turning it back on a student to help them further their understanding of something. And so if I have too much structure, I feel too rigid, but at the same time, right, it would certainly help in many cases to have at least like even like Liliadol has, right, the gradated steps of what are the 50 questions that you want to use for this session, and like say, where do I want to put people, because you can put them at different levels, and you can put them all over the place. Right, you can this group can skip three stages or whatever, and this group can spend a little extra time on something else.
Absolutely. No, 100%. Sorry, I don't want to hog this. Stuckey, if you have anything you want to say too. I feel like, I'm curious your thoughts on any of this.
Sorry, no. Maybe it didn't come through.
Sorry, it just I was saying, if you had any other... I feel like I'm monopolizing the conversation. I don't want to do that. I didn't know if you had anything you wanted to say.
Oh, I understand. Yeah, no, not particularly.
Okay.
As another question, were there any particular techniques or methods that were brand new to you? I wouldn't have thought so, but...
Well, so I hadn't looked at it this way before. And I guess in that way it was new. I hadn't looked at the variation of parameters as being the first order solution, like the integrating factor solution. So when you did this for systems, when you solved the integrating factor for systems, or you solve variation of parameter non-homogeneous equations in first order systems, it was identical to finding an integrating factor. It just, you're using integration of matrices rather than integration and multiplication of matrices, and instead of just single functions. So I thought that was a very interesting connection for me. I hadn't really realized that before, and I think that's a really cool and powerful idea. So it unifies things. It feels less memorization-y, right? Like you were trying to emphasize. So I think that was actually really, really good. I appreciated that insight.
And sorry, can you reiterate one more time? It was using the variation of parameters with matrices?
With matrices was basically the same thing as solving inhomogeneous or first order equations. Like the integrating factor method is basically the same thing as solving variation of parameters with systems. Like that there was a parallel in structure in the solution. And I hadn't like made that explicit connection before. I really appreciated that. So I always thought of that formula and I shrieked in horror.
Yeah.
And then I was like, oh, wait a second, that is reasonable. Yes, that's fine. So thank you.
Yeah, that was mine as well. I don't think that I don't think I ever really learned variation of parameters, and this was a really nice way to see it. And aside from that, I think these were topics that I'd seen or taught in the course before.
Right, and anybody who has taught the course before, in theory, should have probably taught everything that I did. Okay. Certainly the larger structures, right? Like variation of parameters and first, second order systems, homogeneous, non-homogeneous.
I'm sort of curious at the differences, Stuki. I'm sort of intrigued.
So yeah, in brief, aside from ordering stuff, we replaced theories solutions with like discrete systems, difference equations, to try to emphasize that analogy. And then variation of parameters just like it doesn't come up in the course that I taught. Just full stop. Yeah.
So taking the homogeneous solution and multiplying by some sort of function just wasn't a...
Yeah.
Interesting.
That's interesting, yeah. Well, and to be fair, like I didn't focus on that a lot when I taught mine. Like we mentioned it in passing, but I didn't spend significant time on it. So to be fair, now that I'm going through my memory, I'm actually remembering that we didn't like that one. And I know we didn't talk about it here, but there's another thing that apparently a lot of people at my institution like to teach, that is Euler equations, is one that we don't focus on. I didn't focus on in my version, and we didn't do it here.
Yeah.
But I know some like to teach about Euler equations, and they come up in PDEs a lot.
And that is special form of first order differential?
Mm-hmm. Yeah.
Okay.
Yep. Where you have like you have basically an x. What is it? Let's see if my brain remembers.
Y to the n
x
somewhere?
to the r. Yeah, x to the r is usually how I've seen it written, but the basic idea. As
a dependent variable.
Right. So you have a. It's been a hot second since I've done this. That's how on off the. So, I'm not talking about that. I'm talking about sometimes when you have singularities in solutions, you'll have a so x squared dy second derivative ax y plus by equals 0, and you assume a trial solution of x to the m. I'm waiting for Wikipedia here. That's what I remember. So sometimes when you have a singular point at 0, and you have x squared times your y double prime, that causes the having the x to the m solution.
Hmm.
But that's sort of its own thing. I feel like that there's good reason why that shouldn't be in a first course, at least in my opinion. But that's good. That's more of like a second course type thing, or PDEs.
Might be fair, yeah.
But and if you're interested, I can put a link.
Oh, sure, yeah.
Chat if you want to see what I'm talking about. I think this does a fair job of showing the example x squared y double prime plus ax y prime. Sometimes series solutions plus by equals 0. Sometimes you solve these with series, and I know we didn't talk about that either. That's okay. That's its own nightmare. to be honest, the term matching you have to do is and recurrence relation stuff is a bit of a nightmare.
Yeah, sometimes. Well, we have had something like roughly equivalent to this, but yeah, we didn't have a. We did just like a particular constant. Okay, that one. Not that one.
Yeah, that's the one. Anyway, and there's loads of other stuff that you could throw into it.
Yeah.
Like the Voice of Prima book has tons of stuff that like we could have talked about. But like, I mean, there's another favorite topic about like autonomous equations. That's another fun thing that we did a lot more in the class I taught.
Mm-hmm. Yep.
We talked about stability and instability and bifurcations and all of that stuff. So.
Yeah, we spent, I think, a half hour on it, and it was like as a motivator to get to something else rather than its own topic.
Sure.
But yeah, I do tend to like the yeah, I do tend to like the autonomous equations, because here you can get like all sorts of interesting behavior.
Mm-hmm. Right. And for some, you know, these direction fields or slope fields are really cathartic to draw. I don't know why, but I tend to like, you know, there's something cathartic about drawing. So,
yep,
makes me happy inside seeing the particular solution curves and all that. So, anyway. There you
True.
go.
I will try not to get distracted.
Hey, it's your stream. You can get as distracted as you want.
True.
Yeah, I think throughout all of this, trying to get students to link to previous topics, especially anybody who had actually done any work in either pre-calc or calculus with logistic equations. So I tended to bring it up in my pre-calc class, but not spend any actual time on it. Just because it's a really cool thing, but I don't want you getting bogged down with, like, you know, what the exact equation form is or anything like that. I found that a lot of students were getting distracted by that.
Yeah.
Getting really stressed about, oh no, I don't remember exactly what it looks like. And
Yeah.
at some point, when it wasn't my content to shape, I was like, all right, look, I'm gonna give you like the general form. You just have to, you know, tell me what the parts do. Like, what are the function transformations essentially? What are they doing here?
That's actually one we spent a lot of time on, just because of some of my mathematical biology training. we had a lot of biological models based off of the logistic growth pattern, and so like we did actually a ton with ours. But I mean, this is the great thing, is that people focus on different things.
Yep.
And it's fascinating to watch and actually get to see. This is like the professional development I never get to do, is actually sit in someone else's class. You in Penn Center, I get to sit in somebody's class and be like, oh dang, I get to see a different point of view, and this is pretty cool. So,
I mean, that was really my favorite part of your real analysis class. Granted, I had forgotten a lot of the material, being almost 15 years. But yeah, coming in and saying, okay, how is Zach going to present this material in a way that's going to be different to what I would do it as, like, or what the method by which I would do it. So, yeah, I definitely appreciate the differences.
But yeah, it's been fun. I have to say, like, overall, I think I've you know, all the hiccups aside and all just like my own inability to stay the whole time. With all all that aside, I think that we, you know, this has been overall really positive. I hope this kind of thing on our community continues. I really, I'm gonna, darn it, Stucky, you need to do it too.
I know.
You could pull a combinatorics, I'm sure. Like you could.
I'm sure.
You could do it. Or something.
I mean, to your earlier point, Zach, I've toyed around with some things, but I am having a difficult time finding the motivating questions there. And like there's a lot of things that I think the community would be well equipped to just sort of dive into, but I can't find a way to make that dive compelling yet.
I actually had a thought for something in the future. I'll have to DM you because there's something that I think you'd be good at, that like I'd like to be a part of maybe. So like I have an idea for something that I remember learning in combinatorics, but we'll have to talk later because I'm excited. I got excited when I thought of this idea. So,
very nice.
Maybe it'll help. I don't know.
So I know for me, I would have found 1,000 excuses to delay and not do this.
Right.
So I definitely want to thank Zach on getting the ball rolling and saying like,
this is your channel, not mine.
Well, yeah, but you know, you did real analysis, and then I was like, I want to do this. Like that was a self motivation, right? That you ignited.
Well, I'm grateful. That's gratifying to hear, but at the same time, this is your channel and we're celebrating you. Like this is not a so please, you know, all of that aside, as much as I appreciate it, I'm glad I'm the impetus, but this is I think you've done a fine job here.
Well,
really,
thank you.
I'm gratified to see that that you're able to figure out a way to make your own.
Yep.
And I really hope this kind of thing continues. After seeing Penn Center, and I mean, if anyone else does anything, like the reading groups that have spontaneously started.
Yep.
With Dawn
the reading groups
and others.
are awesome. I've only ever really like stopped in for a bit, but yeah, it's just such a great like group of people, and it doesn't have to be formal, right? Like anybody can drop in any particular week. And, you know, they generally have, I want to say 3 or 4 people on the line at any time. Unless I'm completely mistaken. Which is always possible.
I mean, and seeing Cold Gold here, I don't know how you feel about this, Dookie. How do you feel about algebraic topology?
I can't teach algebraic topology.
Oh, darn.
It's very good to say, but...
I thought of you because I was like, well, you know topology well. Better than I do, at least, I feel like. So, my topology is... I didn't take algebraic topology, I just took... So...
I may have to go and look at eventually doing a reading group into this trilogy. The Feynman Lectures on Physics.
Ooh.
So
Those were Those were fascinating. I remember seeing a bit of that before. I think.
yeah,
They're sort of cool.
and it's a very accessible narrative style, just because it's literally him standing in front of people talking. And Feynman was a very compelling speaker.
Mm.
And he certainly was able to get across most of the topics at a fairly... Well, basically he just knew whatever audience he had. It seemed like he always was able to deliver at a reasonable level, no matter who he was talking to. I know in recent years I've especially liked watching Melody Sheep videos on YouTube. This is, in my opinion, the only appropriate use of auto-tune, but it takes... The creator decided to take scientists, and other people too, but scientists giving lectures and talking, and then setting that to mostly electronic dance music. So...
I've never heard of this streamer, or this broadcaster, I guess creator. Let's take a look at it.
Yep. So I'll definitely share a couple in Discord. But yeah, he especially likes physics, and then he's got one that was Mr. Rogers and one that's Bob Ross, that are both just kind of your heartwarming, warm fuzzies for the day.
Yeah.
That's awesome.
And he's got one that's I don't remember exactly how long it is. It's like 2 hours. And it's the history of the universe, where it ticks in time with the music, and then it doubles every 5 seconds.
Okay.
And the amount of time that passes per tick doubles every 5 seconds. And so it gets running real fast. And then you look at, like, all of the all of the stars in the galaxy have gone cold and are now starting to, like, lose cohesion. And you look at the video and it's only halfway over. Oh.
Okay.
That's what we're doing.
Okay.
So,
that sounds intriguing.
the theoretical end of the universe is not even remotely close. It's just, from that point it gets weird.
Sure. Yeah.
All right. If anybody has anything else that they would like to talk about in terms of the class itself, or anything else, I'll open the floor further than it's already been.
Well, dang, I can't give you a clap emoji. I was looking through my emoji list and I can't find a single one. And I'm like, dang, where is it? So we're gonna have to we'll give you a Dino dance instead.
Colon clap. You can usually find all the...
There you go. We'll give you a Dino dance. How's that? The best I can give you.
All right.
I know Dr. Gold has one, but
yep, that's true.
I don't have one of those. So.
Alrighty. Well, thank you very much, both of you, for hanging out tonight and agreeing to come back on for a little bit more, non-content oriented discussion of how things went and whatnot. So I will definitely take some suggestions to heart as we go forward, and if there's anything else you want to contact me with offline, feel free. Anything that you come to realize later. And we'll do some more. We'll definitely try to organize some math ed type stuff, maybe as like a reading group or who knows what.
Sounds good. I'm down with that.
Yeah, you know me.
Of course I am. That's right.
We needed. That's the one disappointment here is that we don't have like this running joke the whole time. I wanted to try and find something about this, but
we needed Danny.
Yeah, that's right.
Yeah. Oh, I will say that is one other. I don't want to say like disappointment, but I do kind of wish that we had people who were unfamiliar with the topic, who were in this class in some way, shape, or form.
Sure.
Still worked out great, but nonetheless, I think it would have maybe helped to have that particular perspective. But we are, anybody who's listening, we are going to be gauging wants and needs for people at all levels, and several of us have decided that we would like to run full classes at many different levels throughout mathematics education. So get in touch with your local streamer and let them know what you'd be interested in, and they'll either be able to do it themselves or point you in the right direction.
Yeah. Well, cool. Again, thank you so much.
Yep. Thank you, Zach. Thank you, Stuki.
Thanks for hosting.
Yep. And we'll open the floor for other questions and let you all have a lovely rest of your evening and week.
Yep, I'm gonna go lurk. But
Alrighty.
Thanks so much.
See you all later. Thank
Take
you so
care.
much. Okay. So, we've got about 17 minutes before Twitch starts complaining that we haven't run ads. So, I would like to open the floor. Unseeable. Unseenable, sorry. Now that you are definitely seeable in the chat, what kinds of differential equations questions do you have? We will definitely have plenty of time for any particular thing you want to talk about tonight. And if anybody else, mixture problems, yes. Yep, definitely. And if anybody else has any other questions about any sorts of math topics whatsoever, please feel free. Drop it in chat. Drop it into Penn Center's Discord. He doesn't mind. He told me. And we can answer these on stream as we get to them. Yes. So... we have... come on, applications. Okay. It's not that far. Autonomous systems, not quite. Was it before that one? Applied first order? No. Oh, yep, actually. Velocity and acceleration, existence uniqueness, yeah. Are we talking mixture problems for one body of water or two bodies of water? Because we can do either of those. We'll start with one, I suppose. So there is a 2 type. However, it is for first order systems of differential equations. So that will probably be at the end of your differential equations class, or it's going to be somewhere in the middle-ish. And I can show you that stuff, but let's not worry about it today. Okay, so we have an intake stream, which is going to input 100, hang on. Okay. What we have here is an intake stream that is polluted. So that pollutant is going to enter the lake. The lake itself has a total volume of 100,000 liters. And it also has an output stream, which will output well-mixed water. Alright, as unrealistic as this is, at the same rate as the intake stream. The intake stream will put in 100 liters per minute. And then we have, again, output is going to be the same. And the concentration of pollutant is going to be, let's do something that's not 100, is going to be 250 grams per liter. Now, as unrealistic as it is, this is going to be an instantaneous well mixing of the water that is inside of the lake. Again, it's not really realistic, but we're going to let it pass for now. Generally speaking, if we're talking about like a tank, it's going to have some sort of mixing fan that's in it. And it'll pull the water out through a reservoir tank, and that reservoir tank is able to have well mixed water approximately. There's some sort of mechanism which makes it work, but we're not going to worry about the mechanics of it. Right, so based on this, we have at time 0, the pollutant in the output stream is let's go with 20 grams per liter. Or has concentration, not just is, but yeah. Right, and we want to find at any particular time throughout this whole thing how much pollutant is going to be within the lake system, or how much is going to be coming out in the output stream at any given time. Our I is 100 minus CI, which is 250 minus R0 is 100. Oh, dash. So helpful in this particular case, the volume in and the volume out are going to be the same. Like the rate at which the stuff flows in and stuff flows out isn't going to change the... Yeah, I got you. Isn't going to change the total volume of the lake. So that is definitely helpful. It is perfectly possible to change the volume of the lake over time if the output stream has like either a function or a particular value that it can output, anything like that. It might itself have a differential equation, which is representing its volume. I'm not going to do that kind of stuff because that's just mean. Yeah, okay. So, my concern, I think, would be what is it that we're going for in terms of... Okay, so you've got R, same as V, right? Rate in, rate out, volume in, volume out, same deal. And then concentration in, concentration out. So yeah, our ultimate goal here, right, is to find out how much pollutant is in there at any time. If we're looking for a, again, typically this is how I do things. This is look for, find function P of t representing the total amount . In the lake at any time, or at time t. Now you could also want to know what the concentration is going to be at any particular time. Right, so let's do both just cuz. So, right, C, our concentration might actually be easier to do first. We know that C of 0 is going to be 20 grams per liter. And C prime, right, the change in the concentration is going to be equal to, here we have our, yeah, well, you could just do it as X over 100,000, that's also P. Oh, that's just, wait, hang on. That's not C prime, is it? That's just literally the function itself. Alright, fine. C of t is going to be equal to just P of t divided by 100,000. So then, yeah, we want to find what is P of t going to be. Just the total amount of pollutant in the lake at time t. So here we get our P prime is going to be our P in minus P out, which, as you said, is going to be the amount that's coming in. So here we have to do unit analysis. P, the amount, is just going to be grams. P prime is going to be grams per, and then here we're using minutes. Right, so then if we want grams per minute, that's going to be our concentration times volume of each of the stuff that's going in and out. So 250 grams per liter times 100 liters per minute. Right, so we get grams per minute, looks good. And then minus, same deal again, but now we've got, as you said, this is going to be P over 100,000 times 100, and again that's going to be grams per liter times liters per minute. Yep, gotcha. So P prime is going to be equal to, here we get 250 hundreds, so 25,000. Right, minus P over 1,000. And then this is where you decide, do you want to do this as a first order differential equation or first order linear, or do you want to do it as a separable differential equation? I'm amenable to either. And in fact, maybe we should do it both ways. Yes, there are two different ways to do this. Now, granted, they are the same way, essentially. And we're going to start an ad break in 35 seconds. So, I'm going to suggest everybody grab a drink, go cycle your water, stretch, do whatever you need to, and we will be right back to do both of these methods. So, see you in just 3 minutes. Which one's easier? That's the question. It depends on you. Oy. I need to work on that. Yep. All right. So if we want to solve this as a linear differential equation, right, bring all the p terms together. And then here we want to assume that the left-hand side is a product rule. Now, as it stands, obviously that doesn't work very well. If you're like, okay, I already know how to do this, yes, dy dx. So we were saying back here, right, p prime is our rate of change in the stuff that's coming, rate of change of the pollution. So we say we have p in minus p out, which was all this stuff. So p prime is going to be equal to 25,000 minus p over 1,000. Or bring the p stuff together. We get p prime plus p over 1,000 is going to be equal to 25,000. And again, if we assume that this is a product rule, yes. Yep. So if you remember your rules, right, this is going to be p prime plus p of x times big P equals your q of x. Right, and in this case we said our mu of x, the integration factor, is going to be e to the integral of little p of x dx. And again, the reason that we want to do that is that we're setting this thing up as a product rule. Shortcuts are worthless if you don't know where it comes from. So welcome to stream. Right, so what we're doing is we're saying here, we want it to be a product rule, so we want this to be mu times p prime. Just that. Jeez, out of shape. Alright, so we've got now a mu p prime plus 1/1000th times mu prime p, where realistically we want the chain rule done and the chain rule is going to get us 1/1000th. Right, that's our goal. So then what do we do with that? Right, this is what we said over here. So our mu, come on, our mu of t, really, because we're doing it in terms of time, and I much prefer to use t for time. It's going to be equal to e to the integral of 1/1000th dt. So e to the 1/1000th t is going to be mu of t, and then mu prime of t is going to be equal to 1/1000th times e to the 1/1000th t. Boop. Oh, stop. Right, so that's our mu. Then we say based on that, take that, and we take that, and we put them together. So therefore, we end up with e to the 1/1000th t times p prime plus 1/1000th e to the 1/1000th t times p is equal to 25,000 times e to the 1/1000th t. Which means, again, our goal worked out. We've got 1/1000th t times p that we're then taking the derivative of, and that's going to take the, come on, there we go. Right, and that's going to get us the pieces we wanted for the top. Right, and that is going to get us. And if you're being picky, ddt. It's going to be equal to 25,000 e to the 1/1000th t. Right. Take the integral of both sides with respect to dt. Then technically this side is now just the integral of the derivative of all that stuff that was in there, which means that it's now just the stuff that was in there. So 25,000 is just a constant that goes at the outside. Here we need a 1/1000th to go on the inside as part of our du up at the top there, e to the u times du. So we need a 1/1000th to be in front of e. I usually like to write this out, even though, right, most people don't. Just to remind myself that, hey, you still need to have this. This part of it, again, ends up being part of that. And then the extra 1,000 is going to be multiplied on the outside of this stuff. So this is now going to be 25 million. And then times e to the 1/1000th t. Plus c. Okay, so then P of t is going to be equal to, here we're going to get 25 million. So 2.5 times 10 to the 7th. Good enough. We're going to divide off e to the 1/1000th t. It's going to go away from the first and the second terms, and then it needs to be divided on to the c. So here this is going to be plus c times, we're dividing it, so this is now going to be an e to the negative 1/1000th t. Levi! Hey, how's it going? My name is Obi-Wan Pez, and this is N Simplex Pachinko. We are doing differential equations at the moment, and if you have any particular questions, you can ask mathy type stuff for tonight. We'll be doing some gamey type stuff on Friday. And hanging out in other people's channels in between. Right, so this is going to be the general solution. And the particular solution we want was, again, that our amount of pollutant was going to have a concentration of 20 grams per liter at time 0. So P at 0. This is going to be slightly different because, again, we had a concentration up above of 20 grams per liter, but that wasn't the amount. Right, so that was going to be 20 grams per liter times the 100 liters per minute of the outflow. So here we're going to have 2,000 grams per minute, which has to be equal to 2.5 times 10 to the 7th plus c times e to the 0, right, times 0. So here this is going to end up with 2,000 minus 2.5 times 10 to the 7th. That's not really a massively significant particular number there, so this is going to be a negative 2.4. That's million. 2.4998 times 10 to the 7th is going to be our C value now. So P of t, the particular solution that we have for this differential equation, ends up being 2.5 times 10 to the 7th minus 2.4998 times 10 to the 7th times e to the negative 1/1000th t. Right, and if we want to just double check, I can factor out a 10 to the 7th just for simplicity's sake, and so this is going to be 2.5 minus 2.4998 times e to the negative 1/1000th t. Right, we need to actually put like y equals here. Right. Times 10 to the 7th. Yay! There we go. Woohoo! -1, 2, like 50, 500, 5,000, 50,000. Okay, too far. 10,000. Good enough. Y-axis is gonna be, man, I don't know. 1 times 10 to the 6th, going to at 2.8 times 10 to the 7th. Right, give or take. Something like that. Times 0, we end up with a value of 2 times 10 to the 3rd, or 2,000. And then this is going to exponentially... technically, right? The distance is going to exponentially decay between our current value, 2,000 grams, and the theoretical maximum, which in this case is 25 million grams. Okay, so unseenable. Any questions on this, whether the process or the graph thereof? All right. Yeah, no problem. So, Levi. X sub n is going to be between 0 and 1 for all n greater than or equal to 1. Cool. For x sub n times 1 minus x sub n plus 1 is going to be greater than 1 for all and greater than or equal to 1. Show x sub n converges. All right. So what class is this for? I have a guess, but you know. Yep, we'll pop exact equations next. Got a couple good examples in here. Right, that x sub n is bounded is given. So yeah, that helps. So x sub n must converge, therefore, right? Or in order to say it converges, we need to show it's monotone. All right, fair. Can say that that is less than 1. So then what's the definition of monotone? Pretzel needs to wake up. There you go. If a sequence is bounded and monotone, then convergent, right? So what's the definition of monotone? What's the definition of increasing? Now, yeah. I think technically monotonicity also includes if it's equal, but we can usually safely eliminate that and say that's not useful. Or equal to. Well, you didn't say that before. All right, anyway. Sure. All right, so a few different ways that you can probably go about it, right? I might suggest, since we know x sub n is between 0 and 1. For x sub n times 1 minus x sub n plus 1 is greater than 1 will imply that 1 minus x sub n plus 1 is going to be greater than 1 over for x sub n. Trade that around, and x sub n plus 1 is going to be less than 1 minus 1 over 4x sub n. Would you be able to use epsilon delta to say that, you know, the next term is going to be like the next term is going to be at maximum a certain size or something like that? I mean, fair. True. Also true. Yep. Hey, Zach. Right. Yep. That's perfectly fair. Okay, so what about this? This makes me think that this is actually going to start... Well... It said converge, so it doesn't necessarily have to be a particular value, right? X sub n plus 1 is going to be less than 1 minus 1/4 x sub n. So if x sub n were large, right, then these values end up becoming close to 1, and therefore x sub n plus 1 is going to be less than that particular value that is slightly less than 1. Right? We can look at it a little bit, see what happens. Minus. Are you allowed to infer anything from the continuous case? Because if you treat this as 1 minus 1 over 4x, you know, y equals that. That's not really true because that's an explicit form. This is an implicit form. Never mind. At what point does this cause problems? X sub n would have to be 1/4. Yeah, okay. So if x sub n is 1/4, this is going to cause problems for x sub n plus 1. Not really, because it has to be less than that. So it'd have to be a negative number. Well, that would be a problem, yeah. So I still think, like, the initial play, at the very least, is to say, okay, let's solve for x sub n plus 1. Yeah, tried using it, okay. Hmm. X sub n plus 1 less than 1. Okay, where did x sub n times the quantity 1 minus x sub n plus 1 less than 1 come from? I'm just playing devil's advocate here at this point. Okay, yeah, it'll eventually converge to a particular x value. Fair enough. 1 times 1 minus x. So x minus x squared. X sub n is less than 1, and x sub n plus 1 is less than 1. Alright, yeah, fair. Ah, okay, yep. Yep. Okay. X is going to have to be greater than a half. Okay. So you know it has to be greater than a half and less than 1, but still don't have something about monotonically increasing or decreasing. Okay. back calculation. All right, fair. I would probably argue that either Ian Stuckey or Penn Center would probably be more well versed in alternate methods, if there are any, or they've seen stuff much more similar to the combinatorics and number theory that you're looking at here. So let's see if we can still work this out for a few more minutes. So need to show that x of n converges, must increase or decrease monotonically. I mean, if you want to make it really ugly, you can make a continued fraction. I don't either, quite frankly, so... So this is Levi's question here, which says that, sorry, we have x sub n between 0 and 1 for all n greater than or equal to 1. And for x sub n times the quantity 1 minus x sub n plus 1 is greater than 1 for all n greater than or equal to 1, and we need to show that x sub n converges. So Levi had said here we have two terms that, since both x sub n and x sub n plus 1 are going to be less than 1, we multiply them together, we're going to get something that is also less than 1. The part that I'm not seeing at the moment, right, okay, hang on. If x sub n plus 1 is also less than 1, then also 1 minus x sub n plus 1 is also similarly going to be between 0 and 1. Right, they're still positive. So that's where you get this stuff, right? So x sub n times 1 minus x sub n plus 1 is going to also be less than 1. Here we have a 4 times that. So this is also saying that x sub n times 1 minus x sub n plus 1 is going to be greater than 1/4. Strictly. So Levi was saying the next step in all of this is that we need to show that this is monotonically increasing or decreasing in order to say that this is going to be be convergent. So right, and he took the steady state. X sub n is going to essentially just be some x. They're going to effectively be the same value. Right, since x sub n minus x sub n plus 1 is going to be negligible. Right, assuming convergence, which realistically we can't really say that. If you're trying to do like a formal proof, you can't really assume what you're trying to prove in the first place. However, it's worth just like investigating it. So you said that 1/4 is going to be less than x times 1 minus x is less than 1. So this is x minus x squared between 1/4 and 1. equals negative x squared plus x. It's going to have zeros at 0 and 1. And 1/4 and 1. What's the output of 1? It's a quarter. Hum. So it's not a particular series. This was just a matter of, or like it is a series, but it's more in the realm of number theory than it is in like Calc 2 or differential equations. Alright, so that's not quite working for us. Math analysis, okay. Yeah, the problem I'm having with this one is that it's always 1/4 or less. Right, the vertex is at x equals 0.5, and then we're getting a value of 1/4 at x equals 0.5. So that by itself is not really going to work. There's something else that's going on there. Yeah, I'm going to say that there might be a problem in trying to assume convergence before you actually prove it. But again, as an exercise for checking behaviors and things like that, it's definitely worthwhile. You just don't want to include it in the final proof. All right, unseenable. Helpful. Exact equations that we're going to go with are 3x squared y squared dx plus 2x cubed y dy is equal to 0. Okay, and then we want to four times x times 1 minus x is not convergent as n tends to infinity. I mean, So I mean, I think like with the other part that we had over here, right? The larger your x of n gets, the larger the overall value x sub n plus 1 gets. You start getting values that are closer and closer to 1. And then when that happens, on the next number, I think that's going to offset it again. And so it's going to end up flipping the other way. Okay. So unseeable. We get here. We want to find the null lines, or the equation that's going to get us the null lines. So we're going to assume, again, some particular capital phi of xy, sorry, psi of xy exists. Such that deep C is going to be equal to 3x squared y squared dx plus 2x cubed y dy. So here we're using the generic derivative operator. This is my favorite one to use. And that's telling us that here, right, we have taken the derivative of x, and here we have taken the derivative with respect to y. Upside EF and upside EY. Upside down E. Oh, I don't know what I call them. So what I say is that there is going to be a particular function in both x and y, psi, which is going to have its derivative taken to get you this stuff. So we say that this thing here is specifically the partial derivative of psi with respect to x only. And this part here is the partial derivative of psi with respect to y only. Yeah. Partial derivatives. Oh. Yeah, no. That's not, okay. Yeah, I just refer to them as taking partial derivatives. They're essentially the same as your dy dx. It's just showing that we're going to take a partial derivative specifically. Yeah, I haven't used a particular word for that symbol. It's also backward. Is it backwards? Yeah, it's also backwards and upside down if you want to go that way. But okay. So we have taken the partial derivative with respect to x and y in theory to get this thing. So in order to prove that yes, this is in fact exact, we have to show that the partial of c with respect to xy is equal to the partial of c with respect to y then x. So we're making the claim that this is psi sub x and this is psi sub y. That's a claim at this point. So then when we want to show that, yeah, in fact they are, and they do form an exact equation, what we do is we say, okay, we've got to take the partial with respect to y of psi sub x, which is going to be the partial with respect to y of 3x squared y squared. Right, and then we lop off the dx portion. We just say, okay, we don't need it right now. Again, we're just taking the partial derivative with respect to y of that stuff. So here, this is going to get us a 3x squared times 2y, which is going to be a 6x squared y. And then, over here, we take the partial with respect to x of c sub y, which is 2x cubed y. Oop, derivative. Partial with respect to y, with respect to x, damn it, of this thing, which is going to be 2 times 3x squared times y, which is going to be 6x squared y, which, lo and behold, it happens to work. Woo! That's the part you're confused on, taking the derivative to y when there's an x in the equation. Okay, so partial derivatives. X and y are not functions of each other, ever, when you're talking partials. What we're saying is that here, in this particular equation, psi of xy, both x and y are independent variables. Both x and y are independent variables. So here we're talking like space, right? So if I want to know what the temperature in this room is at any point and at any time, right? If I want a temperature function of any point in this room at any time, my independent variables are going to be time, x, y, and z. Right? All 4 of those would be independent variables. So that gets to be pretty wild. And then here, your temperature is the only dependent variable. So, if I want to say, what's the temperature in this room with respect to x only, what I'm going to do is I'm going to take all of my time, y, and z coordinates and call them constants. And just say, with respect to x only, is there a particular pattern going across the room this way for that temperature? And as it turns out, right, if there is some sort of algebraic function, yes, you can do that. You just say, again, in here, we're going to assume that our x is the only variable that matters. Y is just going to be a constant. So treat y the same as you do the 2. So kicks over there. If there's no x but only y, does that? Yes. Because if you're saying, I only want to look at how it changes in this particular direction, and then something says it changes only in this direction, you could just be like, well, that doesn't matter. Or only in this direction. Or only through time, right? That particular location only changes through time. Then you don't have to care about it. It's not going to change with respect to x. Yeah, so you have to have the variable you're taking the derivative of, otherwise it's just going to get knocked away, turned to 0. I do have another example here somewhere, I'm sure. Yeah, cool. Right, so if we had 6xy plus 3 plus parentheses 3x squared minus 7 times y prime is equal to 0. Right? If it was written like this, you'd want to change this first. 6xy plus 3 plus parentheses 3x squared minus 7 dy dx is equal to 0. And then here, you're multiplying it over there too, but nonetheless, it's going to get multiplied over here as well. So that, don't put it there, put it here instead. Right? So then again, for this, we'd want to check if this is with respect to x. This, my claim is this is phi sub x, so therefore I want to take the derivative with respect to y of phi sub x, and then we get, again, partial with respect to y only of 6xy plus 3, which is going to be equal to 6x plus 0. Right? And then over here, same deal. We're going to claim that this is phi sub y. Therefore, we need the partial with respect to x only of phi sub y, which is the partial with respect to x only of 3x squared minus 7, which is equal to 6x. So this is an exact equation. Yep. The 3 here and the 7 here both become 0 because there is no term of the variable in question. Yep. So my point is that I want to split y prime into dy dx and then move the dx portion so it's no longer on the bottom. I want this to be equal to the derivative of psi as a generic derivative. So we have to take the derivative with respect to every possible variable at some point or another. And in this case, it just ends up being x first, then y second. sorry, this portion, we have partial with respect to y of 6xy. 6x is a constant, it comes out. Y is the variable, and we do the variable thing, right? We take the derivative of y, and it's just 1. So that's now 6x times 1 plus 0. We're on an ad break, so unfortunately, y'all are going to take a little... Can we do that? Maybe. Yes, 60 seconds. 1 minute. Okay, apparently it's going to continue for another minute and a half. I don't understand. Yuck. Apparently wanted to run a whole 3-minute. Yeah, apparently we're just having a little bit of fun here, so apparently Twitch wanted to run a full 3-minute ad instead of listening to me. So we're just gonna kill another... Goodness. We back? Alright, I think we're back. These are 500-gram Eskrima sticks. They are heavy as shit. And really solid. So we've been doing a thing for Eskrima. It's a Filipino martial art that is designed to be used with machetes to defend oneself against typically like gang members, criminals, etc., as is usually the case with martial arts developed by, random people to try to help safeguard your average person. So we've been doing something lately in our class where we use 2 sticks and we both get in the same stance and we strike out first like this, and when we do that, it's going to hit sticks together and then bounce back to the other side. We're going to strike out underneath, and that's going to strike the other person's stick as well because they're doing the same thing. And then, so it's a 1, 2, 3. They switch positions. 4. Strike again. And then, what is it? 1, 2, 3, 4, 5. So it's really awkward because it's a 5 count, and now we're mirrored on this side. 1, 2, 3, 4, 5. So typically it actually ends up only, because you only have 3 actual points of contact, 1, 2, 3. You tend to count in 3s instead of 5s, but it's really weird. And then we start doing all sorts of weird shortcuts where you typically don't actually end up doing the 3 count or the 5 count. It's just kind of like you kind of do a bunch of things that are close to it. Ugh. And now my thing over there is now saying that we're on an ad break because it was queued up exactly the same as... Whatever. This thing doesn't know what it's doing. I threw my glove somewhere. Is it? Oh, okay. No, it's right here. It's the problem with like everything in here being black. It's all the same color. All right. So, my point, Unseenable, is that what we have is that we're assuming that there is one function, which is a multivariable function, c of x and y. So, given that it is a multivariate function, we're going to take a generic derivative, just d, right? That is the same as doing that is actually the same as doing nabla, which is the upside down triangle. So that is our... Technically, this is also like a vector, so maybe we don't want to go there, but... Oh, fine. Thank you. So using nabla of c is going to be the same as the generic derivative operator. We're going to get every individual derivative done separately. So we take... This is... right, the partial derivative with respect to x plus the partial derivative with respect to y. And if we had more variables, we'd also do that. Now, I just do it as the generic derivative operator d, and that's perfectly fine. It does the same thing. Okay, so the point that I was making was that here we've already done the partial derivative with respect to x and the partial derivative with respect to y. At least, if it is an exact equation, we've already done it. And so the claim is that those are the partial derivatives with respect to x and y, respectively. And now, if we take their partial derivatives with respect to the other variable, we should get the same thing in both places. This one over here. Right, so this, again, technically, it's listed as being y prime, which assumes that y is dependent and x is independent. But if we're going to say, wait a minute, what if it's not dependent, independent? What if this is in fact a multivariate function where x and y are independent variables? What we can do is transform it into this particular form with dy here and dx here, separately from each other. And when we do that, we're essentially trying to separate variables But the only thing is that we're not going to be able to separate the variables entirely. We've got an x squared that's inextricably linked with y, and a xy that's inextricably linked with dx. So we're never going to really separate variables. But we can say, wait, let's just make it a multivariate function. So shift your perspective. Instead of y of x let it be psi of x comma y. So now psi, you can let it be a dummy variable if you want, right? Psi is going to be this dummy variable where x and y are both independent. Right? This is dependent, this is independent. We're essentially parameterizing and saying that psi is going to be our dependent variable, and both x and y are going to be independent variables. I certainly hope it's not raised to the dy, but I get your point, yeah. So we have a dy that's attached. We also have a dx at the bottom, but instead we multiply it through. It gets turned to 0 on the other side. And if there's another term there, move it over with the other terms that don't have anything, and then magically it becomes part of the dx term. All right. So no matter what we're doing at this point, we look at this and say, okay, now we've got a multivariate function, psi, that is going to have the first part here with respect to, that has had a partial derivative with respect to x. Here we have a function psi, which has to be the same psi as over there, but this one has had the partial derivative with respect to y taken. It splits into two parts, verification and then discovery. Verification is just showing that, and that's the part that's down below, yes, this is an exact equation, which means that there is a psi function which does exist. So in this case, and in both cases that we see here, since it is exact, some psi of xy exists such that nabla of psi is equal to the stuff up there. That was 6xy plus 3 parentheses dx plus 3x squared minus 7 dy. Okay, so the question is, are you okay with that? Right, so step one, oops. Verification. Yeah. So all that stuff is just verification. Step two is going to be solution, or whatever I said before. I don't have any actual names for it. It's fine. So in the solution portion, we say that this stuff is psi partial with respect to x. Therefore, we could take the integral of 6xy plus 3 with respect to x. Again, this is partial, really. And so what does that do? Well, again, here we need to worry about the x's, and the x's only. So y is going to be treated as a constant. Ignore it. We now have an x here. When we take the integral of x, we get 1/2 x squared, or the 2 from the 6 is going to get absorbed into the x squared. So then we end up with a 3x squared y plus integral of 3 with respect to x is going to be just 3x. Then we now need a constant, but it's not just any constant. It is a constant with respect to x, which means that it is allowed to be any function with respect to y only. Okay, so this is psi now, which has to be the same on the other side when we take the partial integral with respect to 3x squared minus 7 partial dy. Which again, 3x squared is a constant, so it just becomes 3x squared y minus 7y plus some function that is exclusively of x, g of x. So when we equate both sides, we say, okay, we've got now 3x squared y on both sides. Those can be eliminated out from, not like literally just eliminated, but these are going to correspond, and therefore they're not going to be part of the next equations. It's just basically a verification to make sure that, yeah, they are, in fact, the same, right? We've got something in terms of x on the left, something in terms of x on the right. Therefore, this is going to be 3x is equal to g of x. And something exclusively in terms of y over on either side here, which is going to be f of y is equal to negative 7y. There's nothing left, so we're good. This says that according to both of these, we have it that psi is equal to 3x squared y plus 3x minus 7y, and that can be equal to any constant we want. Now, the really cool thing about this is that you can get something like Desmos to actually graph this for you. Oops. X squared y plus 3x minus 7y. Right? Yep. Okay, is equal to c. We're going to go home with this and add a slider for c. If c is 1, then we get something that looks like this. And in fact, let's thicken that up a bit so that everybody can definitely see it. If we change the value for c to make it higher, we notice that these points over on the right start moving closer to each other, and then eventually they actually split the other way. And we get a different type of rational function. This is a rational function. Albeit a complicated one, but nonetheless. This is another kind of rational function. This is yet another. And I think these are probably symmetric. Anyway. And then we can play. Right, it'll just automate it, run back and forth. So this says if our C value, our constant, is any particular value that we have here, it's going to make this particular graph, right? C equals 5.09 gets us this particular rational function type graph. Right, and then we could look over and yeah, we didn't have any initial values or anything like that. So this is just telling us that this is in fact our psi function as a function of xy. And it can be equal to any constant c. Now we could also do the other one, right? This was a verification step here, and then now we want the one verification. We got the answer we were looking for, and then 2, we go for solution. So, again, our c with respect to x is equal to 3x squared y squared dx. So then we could just take the integral of both sides with respect to x, again, partial. So c is going to be equal to, here again with respect to x, x squared, 3x squared, take its integral, it's x cubed. And then the y squared is just a constant. And again, plus any constant, which is going to be a function of y alone. And then do the same on the other side. So integral c sub y is equal to integral of 2x cubed y dy partial. So c is going to be equal to, here again, x cubed is going to be left alone, 2y dy, we integrate with respect to y, it's going to be x cubed y squared plus some function of x alone. Now here's the fun part. Right? We got a function with x's and y's, so that is definitely part of psi. But then we've got functions of x and y alone, which have no corresponding parts on the other side. So therefore, this is it. It's just c is equal to x cubed y, y squared, which is equal to some constant c. And then that's it. All right. Yeah, so Unseenable, I hope you have a decent time with your exam. I don't think it should be, awful. Try to look at, and I know it's kind of late to start on it, but try to look at all of the little pieces and try to understand where they're all coming from. And if you get that kind of bigger view of everything, it fits. All the puzzle pieces fit so much nicer. Not as bad as Calc 2. I agree. Calc 2 was, yeah, that was a bit harsh. My biggest problem with Calc 2 is, as a student, I was constantly guessing. As an instructor, I was constantly trying to not make people memorize stuff or get people to not memorize stuff, because those are two different things. And it wasn't until I started saying, like, okay, what are you integrating? Like, what's the point? Break it up into a sum, right? Show me your slice as a sum. What is it that you're doing? Oh, you're finding the volume? Cool. Find the volume of this shape. How do you do that? Cool. Now, how does it change as it moves? Okay, that changes the, radius of this semicircular thing. So 1/2 pi r squared is going to be your area, and then its thickness is going to be dx, and then your radius changes as a function of x. So it decreases this way, it increases that way, etc. Had to take it as a 7-week course. Yeah, that could be. I can imagine. Oh. What we got going on tonight here? Okay. Absolutely. Let me restart Pretzel again. It apparently does not like me today. Nice. Okay. So existence and uniqueness. What do you know? Very broad. That is not what I hit, but cool. Megalomorph! Good evening and welcome. Might have missed the last 15 or so differential equations night. Did you miss anything important? Yeah, I mean, like the whole class, but it's fine. We were talking tonight just about like different things that we might have changed or different things that we were talking about. And yeah, Zach and Stuki both brought up the fact that we have slightly different empathoning of the objectives because I had moved all of our second-order differential equations to being after first-order systems as a motivation technique. They'd never really seen that before. I have to thank Pavel Grunfeld from Drexel University for doing that for me. He gave me that inspiration, and I was like, that is absolutely amazing. And so I was able to run with it a bit. They both said variation of parameters with matrices. Zach had noticed was roughly the same as looking at first order differential equations with an integration factor. And I was like, well, turns out. And actually, that is the same as what I'm talking about with unseenable. We had talked about over here, right, doing exact equations. If we look at exact equations, we could actually figure out a particular mu function that will turn both of these things into an exact equation. Right? So there is an actual way to do it so that this becomes an exact equation if it isn't. And if we simplify it by saying, let's assume that mu is not a function of both x and y, but only of x or only of y, then we can simplify, and it turns out that that is a way to come up with an integration factor for exact equations, and also it backs up into simplifying it again into making an integration factor for first order linear systems, or first order linear differential equations. Yep. Yeah. I typically don't use the matrix exponential notation just because a lot of students get confused about it, and maybe they need to get over it and do it some other time, or, you know, just so that they can use it in future classes. But I don't like using it on our first class, you know, first differential equations class. Okay. Pretzel's gonna keep doing this on me. Man. Alright, let's reload. Reload the tab, see if that changes anything. Alright, so unseenable, how do we show that there is at least one solution for any particular differential equation? Now, if we're looking specifically at first order linear, right, this is y prime plus p of t times y is equal to q of t. So not immediately, but we'll get to an actual example in a minute. Right, so if we're looking at a particular differential equation, right, this is also potentially looked at as y prime is equal to q of t minus p of t times y. So, like, talk to me about this slope, y prime, right? when is it going to have some sort of actual value? So when is that, when are we going to get a differential equation, y prime is equal to that stuff, that has a solution? Or if you want to go the other way, where are the problems that are going to exist? Right, so finish the sentence if you want. We're always going to have valid slope values, y prime, provided what? Okay. So if you think back to like our slope fields and stuff like that, right? Y prime is equal to something. In this case, we've got a function of both t's and y's. So this is like, f of t comma y. And if we think back to how this was done with our slope fields before, all that we really cared about was that this wasn't going to create anything that had either stuff that doesn't exist at all or isn't vertical. Right? If we have a vertical slope, then we have potential existence problems for solutions to differential equations. Could end up being that this is at a vertical point. It could be a singularity. It could be an asymptote. It could be a whole bunch of stuff. So we have to take those individually one by one and determine what's going to happen. And the problem with actual vertical values, right, is that once it goes vertical, it's going to stay vertical unless it changes according to y. In this particular case, right, it's possible. But the problem is that if Q of t or P of t don't exist or have infinite value at one particular t value, then they're going to get locked in. They can't then move at all. They will have a vertical asymptote. They will have a vertical stable solution. Shouldn't say stable. It might be unstable. So as long as P and Q are going to be continuous on T belonging to some interval. So usually we would let that be an open interval alpha to beta. As long as P and Q are continuous on that open interval alpha to beta, then we're always going to have these valid slope values on that same interval. So that is going to show an existence of a solution. Right? There must be at least one solution provided P and Q are just continuous on this open interval. All right. How about uniqueness? How can there be more than one possible solution for any particular differential equation? Well, again, you've got slope fields that we're talking about here. So like if I give you a slope at a particular point, it's going to then lead to another slope at a particular point, which then leads to another and another and another. It's really deterministic, right? It can't give you multiple different values because these are functions. We've already dealt with this stuff when we were doing pre-calc. Right? As long as P and Q are continuous functions on that same interval, there can only be one possible solution. So when we're talking about first order linear differential equations, it's really a matter of right? If P and Q are continuous functions, on an open interval, I, alpha less than T less than beta, containing our initial point T equals T0, then there exists a unique solution y equals u of t that satisfies our differential equation, which again, y prime plus p of t y is equal to q of t. For each t in the interval, and satisfies the initial condition. Y of t0 is equal to y0. So this first order linear differential equation definition really works with both existence and uniqueness. As long as p and q are continuous functions on some open subinterval or some open interval alpha to beta that contains your initial point t0, then there's going to exist a unique solution on that particular interval, and it has this initial condition y of t0 is going to be equal to y0. Okay, so like, what does that all do in practice? Obviously, you can't just like okay, so if we go like this and we say, let's do first order linear cosine x y prime plus sine of x times y is equal to x squared. Now the sine of x and the cosine of x are their own things. They are not the cosine of parentheses x times y prime or sine of x times y. This is cosine of x times y prime plus sine of x times y is equal to x squared. And initial condition y of 0 is 4. Okay, so since this is a first order linear differential equation, how do you know? Well, the only derivative here is y prime. There's only one of them, so first order. And we say it's linear because looking at all of our y's, we have y prime, we have a y, and with all y's and its derivatives, the only thing that's attached to it is a function of x. Right? Now that function of x may be a constant, it may be 0, but nonetheless, right? Y prime has a cosine of x. Y has a sine of x. They are functions of x alone. So we're good with this. Okay, now we want to trade this in for our other form. Y prime plus p of t times y is equal to q of t. So here, this is going to say, okay, y prime plus sine of x over cosine of x times y is equal to x squared over cosine of x. Again, same initial condition. So, we say here, well, okay, sine over cosine is going to be a tangent of x. And this thing over here is going to be an x squared secant of x. Either way, cosine's on the bottom, and this is going to be discontinuous. At x equals, right, where is cosine of x going to be equal to 0? This is going to be any odd 2n plus 1 pi over 2 for n being integers. So this means that we do have a subinterval, which is going to be between negative 1 pi over 2 and positive 1 pi over 2, which contains x equals 0 This is the maximal subinterval over which this particular differential equation has functions p of x, tangent of x, and q of x, x squared secant of x, continuous. Hey, Punching. We're looking at existence and uniqueness of first-order linear differential equations. So here we see that as long as our cosine of x in either of these fractions is not equal to 0, we have a continuous differential equation, or continuous functions that are a part of our differential equation. And so this is going to make it, again, x equals 0 is going to be between negative pi over 2 and pi over 2. So we have a unique solution on x going from negative pi over 2 to pi over 2. And I believe that's it, right? As long as, again, as long as our initial condition is within those x values, then we're good. Okay. So then what about nonlinear differential equations? Well, doesn't quite work as nicely as that. However, it's still going to be, like, not awful. Okay. So, A. If f is continuous, and again here this is going to be y prime is equal to f of x comma y. So it can be a function of x or y, but nonetheless it's going to be set up in this form. So if x is continuous on a rectangle, x going from A to B, and y going from C to D, that contains our initial point x0, y0, then the initial value problem, y prime equals f of x comma y, where y at x0 equals y0 has at least one solution on some open subinterval of x going from A to B such that x0 in AB. Normally I put x being a member of that interval, but you know, we have a specific x0 which needs to go in there. Anyway, and part B, if both f and df dy partial are continuous for all real numbers, then y prime equals f of xy, where y at x0 equals y0 has a unique solution. On an open subinterval of x0 belonging to AB. I don't need and there. It's just, right, the existence proof's the beginning. The uniqueness proof is the second part. Okay, so y prime is equal to x squared plus 4 divided by 8y minus y squared. Okay, so our f of x comma y is going to be that fraction. Right, and this is going to have continuity where 8y minus y squared is not equal to 0. So therefore y times 8y, nope, y times parentheses 8 minus y equals 0 is going to cause problems. And so this is going to split things up into y intervals of -infinity to 0, 0 to 8, and 8 to positive infinity. Right? Could have some sort of connection to that. So there will exist some solution on each of those subintervals, depending on what your initial value is. Right? That's not necessarily particularly helpful, but nonetheless. Okay, now if we try to take the derivative of this thing, right, f prime, nope. We just want this to be f df, come on. Right, df dy as a partial derivative. The numerator is just a function of x, so it is a constant. The denominator is just a function of y, so we can say that that whole thing is going to be right, that raised to the negative first power. So the -1 will come down front. We leave the x squared plus 4 because it's a constant with respect to y. And put that over parentheses 8y minus y squared, all squared in the denominator. Right? The derivative of 1 over x is going to be a -1 over x squared. And then we have to do chain rule. So we multiply all of this by the derivative with respect to y of 8y minus 8y minus y squared, which is going to be 8 minus 2y. Continuity here is the same as the other side, so that's it. There's nothing else to really do here. Right, we are continuous on x going from negative infinity to positive infinity. And y can either go from negative infinity to 0, or 0 to 8, or 8 to infinity. So we could also draw this 0, 8. Right, so our theoretical rectangles gonna look like that. Alright, so unique solutions are guaranteed to exist on some subinterval of each of those regions by the uniqueness or existence and uniqueness proofs given above. So we take some function that we have. Again, this is a nonlinear differential equation. And we say, all right, given this nonlinear differential equation, what's the continuity of it? It has to be between negative infinity to 0, 0 to 8, or 8 to infinity. Okay, so that guarantees that some function exists on each of those subintervals somewhere on them. Then we say, okay, if we take the partial derivative of our f above, that's going to get this thing, and then the continuity ends up being the same in the y direction, and the continuity in the x direction is also the same. It's just x squared plus 4. You can have that be anywhere. So, as it turns out, right, we're going to get continuity on either negative infinity to infinity by negative infinity to 0, or negative infinity to infinity by 0 to 8, or negative infinity to infinity by 8 to infinity. Alright, now those rectangles are infinitely large, and that means, altogether, that unique solutions are guaranteed to exist on some subinterval of each of those regions. So if you pick an initial value that exists in the bottom section, then there has to exist a unique solution that goes through that one point. In the middle section, you pick a point, I could potentially show you one unique solution that is guaranteed to exist that goes through that solution. And same with the top. You give me an initial value, I will show you the one unique solution that is guaranteed to exist that goes through that point. Hey Silver, how's it going? Woo! Alright. Anybody else have any other questions? They are both unique and exist. Yeah, we've been doing all sorts of stuff lately. We got, yeah, cool. Still need to submit for a trivia league before like 7 o'clock tomorrow morning. It's fine, as long as I remember to do it before I go to bed. Elite Dangerous just got done with a big event. They got done early, which is not really a surprise because it was a combat event. When they ask you to haul stuff, forget it, but you know, sounds trivial. Oh, my brother just started playing Outer Wilds. Hey, Sensation. Hello there. How's it going? Yeah, so my brother just started playing Outer Wilds, and I messaged him. I was like, dude, if you need a rubber duck, I'm your guy. Because I would love to talk Outer Wilds, and also I can do it without spoiling you. Given also how deeply I've gone into the lore of it. I named the main character. And as soon as I did it, I started, like, tearing up. It's just one of those things. If you know, you know. Let's see. Yeah. So we're officially done with our differential equations class. that we did here. I would like to gauge a few of the community interests and trying to see what kinds of content people would be interested in. So I may end up putting some polls up in Penn Center's thingy. And asking if people are interested in pre-calc, calc, calc 2, calc 3, differential equations, linear algebra, analysis, higher stuff, or indeed lower stuff. If we end up with a lot of community requests to do said particular, oh, MATLAB, hot tub MATLAB, dangerous. Maybe not dangerous to the people, but definitely dangerous to the electronics. College football 25, bring your alma mater back to relevance. Nice. Discrete calculus. Is that also called numerical methods? No, okay. That's fair. The only reason I ask is that I have this particular numerical methods book over here. Actually, this is even different. This is Numerical Solutions to Ordinary and Partial Differential Equations by L. Fox. Discrete calculus is sums and finite differences of sequences. Okay. You know what? Zach is doing infinite series, which is close, I think, asterisk. I think he was covering at least some of that material. You could ask him more directly. Or if that was his next class that he was planning. Or at least part of it. I don't know. Maybe. Alright. Hated Calc 2, loved 1 and 3. Yeah. It's not really surprising. So many people are also in agreement. Fractals and dynamical systems might be fun. Yeah, that's true. All right. Boo. We are going to go and see. we're gonna go see Irish John Games, I think, who's currently doing a partner push and is working on game development. Jern Jam is his larger kind of, not exactly organization, but something that he's been doing lately. I will be back on Friday for more games type stuff. We will also be going to do some more mathy type stuff as of next week. I don't really have a plan for it, but at the very least Tuesday, I'll probably be here Monday and Wednesday as well, but just for other reasons. I don't know. We'll figure it out. I may decide not to do it, so it's all good. It all depends on, I think, what other people are up to. I may also do some Zelda or whatever else. I feel like whatever the community needs are in the moment. So, at any rate, I will see you all a little bit later, and I hope you all have a good rest of your week. See you on Friday. See you in other people's chats. See you lurking and all that other good stuff. My name is Obi-Wan Pez. This is N Simplex Pachinko. We are officially done with Differential Equations. Thank you so much.